Hi, this is Professor Collins again. We're going to talk a little bit more about the material in Chapter 10, specifically alternate theories or additional theories of chemical bonding besides Lewis structure, and those are specifically valence bond theory and molecular orbital theory. Instead of saying they're alternate theories, I think we should call these new theories additive because one theory is not exactly right, but it leads a lot of credence. Let's talk about the problems associated with Lewis bond theory. We know a lot of good things come out of Lewis structures, but it does have some problems. It predicts general property trends very well, and however, it does not give good numerical predictions on bond strength and bond length. The second point is it's a great first approximation, not a good one, but a very good one, of the bond angles, but it's not very good to determine the actual bond angle in a compound. So it cannot explain concept of resonance. You can draw resonance structures, but it doesn't adequately explain the concept. And it does not predict very well the correct magnetic behavior of molecules. That's something that the theory called molecular orbital theory, MO theory, does on a better basis. So as I said, in addition to Lewis bonding theory, we have these other two theories that give us additional information and sometimes better for certain aspects of molecules. Valence bond or VB theory states that the electron density of the valence electron is localized between the bonding atoms. And then you have hybridized orbitals that overlap to form molecular bonds. MO theory states that the electron density of the valence electrons is delocalized, and the valence electrons occupy molecular orbitals that spread throughout the entire molecule. Valence bond theory, VB theory, involves the overlap of atomic orbitals to form molecular bonds. So it basically uses VSEPR theory, valence shell electron pair repulsion theory, and the concept of hybridization to explain bond formation. We'll talk more about hybridization soon. But a molecular bond results when electrons in their atomic orbitals overlap. And the key point is that the hybridized atomic orbitals are formed. The valence electrons in an atom reside in either the quantum atomic orbitals or the hybridized atomic orbitals. When we mention the term hybridization of orbitals, we're talking about S and P and D orbitals that we're familiar with in terms of electron configuration, but they come together to form hybridized orbitals. The hybridization is the transformation of the central atom's atomic orbitals to accommodate valence electrons from the bonding atoms. The type that occurs in the central atom corresponds precisely to the electron pair geometry of the compound. The electron pair geometry having 2, 3, 4, 5, or 6 centers of electron areas of density. Remember, a compound's electron geometry is determined by the number of bonding atoms and non-bonding. Bonding atoms are lone pairs surrounding the central atom. So in the summary of the hybridization types are shown at the bottom. If you have electron geometry that's linear, meaning do you have two areas around the central atom, you're going to have sp hybridization. If it's trigonal planar, where you have three areas of electron density, you have sp2 hybridization. Tetrahedral, or four areas, is sp3. Trigonal bipyramidal, or 5 orbitals, is dsp3. And octahedral, where you have 6 areas of electron density, is d2sp3. Now it's easy to associate the hybridized orbitals with the electron geometry. Going back to the top of that list, linear, where you have 2 areas, that's basically one S and one P coming together to form an SP. Trigonal planar, where you have 3, you have one S and 2 P's coming together. Tetrahedral, you have one S and 3 P's coming together. Trigonal bipyramidal, you have one D, one S, and 3p's, or a total of 5, coming together. In octahedral, you have 6. 2 Ds, 1 S, and 3 Ps, or a total of 6. So the hybridized orbitals, the sum of the number of them equal the number corresponding to electron geometry, electron pair geometry. Let's look at the valence bond theory and hybridization of methane, CH4. If you look to the left, you can see how the valence electrons, how they feel according to principles in the 2s orbital, and then each the same direction, parallel directions, in the 2p orbitals. That's your standard description of electron configuration for carbon and its 4 valence electrons. Well, valence bond theory treats those 4 valence electrons equally and creates hybridized orbitals, resulting in 4 sp3 hybrid orbitals having energy levels somewhat between the s and the p to the left. But they're equal in energy level, and that seems to be the case because when you form the carbon, the methane molecule, 1 carbon and 4 attached to 4 hydrogen atoms, they are equal in energy and length. So it makes sense that they would all have hybridized orbitals of equal energy. Here's another summary of the electron geometry and its related hybridization. When you have 2 electron groups, you form a linear geometry. The hybridization that we just began discussing will be sp orbitals. 1 s orbital and 1 p coming together to form sp. If you have 3 electron groups, trigonal planar, 120-degree angles, you're going to have 3 equal sp3 hybrid orbitals. Instead of 1s and 2 p's, you have 3 sp2 hybridized orbitals. Tetrahedral with 4 electron groups, like methane, the previous slide, forms 4 equal sp3 hybridized orbitals. 5 trigonal bipyramidal, you have sp3d hybridized orbitals, 5 of them. An octahedral with 6 forms sp3d2 hybridized orbitals. So we discussed sp3 hybridized orbitals and the formation of 4 equal sp3 hybridized orbitals for methane, CH4. Let's talk about hybridized orbitals that form double bonds. And that takes place when you have sp2 and sp. So sp2 hybridization is seen with double bond formation. So is sp. That's in triple bond formation. Double bonds come from 4 electrons or 2 pairs. Only a few elements can really double bond: carbon, sulfur, nitrogen, oxygen, and phosphorus. And we say they have sigma and pi components. Now the sigma bonds represent the single bonds that take place between the atoms in the plane of the bond. The pi bonds are associated to that second bond, the double bond, or in the case of triple bond as well. The pi bonds extend above the plane of the bond and below the plane of the bond. So they're at right angles to the bond itself. And they result from the unhybridized p orbital. Let's look how pi bonding forms in the molecule formaldehyde with the formula CH2O. We know that CH2O will be trigonal planar. There's 3 areas of electron density around the central atom. The valence electron diagram for those elements is shown at the top. What will happen in terms of hybridization theory, VB, valence bond theory that includes hybridization, is that 3 sp2 hybridized orbitals will come from the valence electrons in carbon. There's typically 4. We think of them as going both 2 in the 2s orbital and 2 in the same position in the 2p orbitals. But after being hybridized, you have 3 sp2 orbitals, hybridized orbitals, that will form the sigma bonds from carbon to hydrogen, oxygen, and and 2 hydrogens and 1 oxygen. These hybridized orbitals at the sp3 will form the sigma bonds. The pi bonds are formed with the 1 electron and the p orbital of carbon, as well as along with 1 electron in the p orbital of the oxygen atom. So in this illustration of formaldehyde, you can see that 3 sigma bonds are formed from the carbon atom. There's 2 to each hydrogen atom, and there's another sigma bond, sp2 sigma bond, formed to the oxygen. The double bond is the result of the pi bond that's formed in the unhybridized orbitals of carbon and oxygen, the unhybridized p orbitals. Now in triple bond formation, you have sp hybridization seen. You have 6 electrons formed, 3 electron pairs in a triple bond. Only a few elements can do that: carbon, sulfur, nitrogen, and oxygen. You have 1 sigma bond formed in the plane of the bond, and 2 pi bonds above and below at right angles to the plane of the bond. So you use hybrid orbitals for the sigma bonds, and you form pi bonds using 2 sets of unhybridized p orbitals. So in the previous slide we saw where we used 1 unhybridized p orbital from the central atom to form that double bond. Now we're going to form 2 additional bonds to the sigma bond, 2 additional pi bonds that will be above and below the plane of the sigma bond. And as I stated, you can see here where 1 s orbital and 1 p orbital combine to form 2 sp orbitals. Again, as you can see here, you have 2 sp orbitals formed and 2 unhybridized p orbitals. That will form the 2 unhybridized p orbitals will contribute to the pi bonds above and below the plane of the sigma bond. So in the molecule acetylene, which is C2H2, you have the triple bond in the middle, which consists of 1 sigma bond and 2 pi bonds, a total of 3. Continuing on, sp3d hybridized orbitals are formed when you have 5 electron area groups around the central atom, and you form hybrids with 5 separate orbitals, 1s, 3 p's, and 1 d, to form 5 sp3d hybridized orbitals. And you have additional unhybridized d orbitals. And this is an example of a sp3 hybridization of arsenic pentafluoride, where you have 5 electron areas around the central atom. You form hybridized orbitals, sp3d, 5 of them, that form sigma bonds between the arsenic and each of the 5 different fluorine atoms. The Lewis structure is shown on the left, the valence bond model shown on the right, showing equal sigma bonds between the 5 ASF bonds. And lastly, we come to electron geometry of 6 octahedral, and equal energy hybridization occurs to form hybrid orbitals using 1s, 3 p's, and 2 d's to form 6 equal energy sp3d2 hybridized orbitals, as shown below. Here's an example of that. The Lewis structure of sulfur hexafluoride. Sulfur hexafluoride shown on the left, and on the right you see the valence bond model showing 6 sigma bonds formed with 6 sp3d2 hybridized orbitals. Let's predict hybridization in each of the different, around each of the central atoms in the amino acid glycine. You see on the left the Lewis structures and the electron pair geometry associated with each of those. Let's relate that to hybridization. Starting with the nitrogen atom, you have trigonal pyramidal. Around the first carbon atom on the left, you have tetrahedral. Around the second one, carbon, the one facing to the right, you have trigonal planar, and the last central atom, oxygen, has a bent geometry. Here are shown the results. Even though they may have different molecular geometries, hybridization is simply based on the electron pair geometry. So looking at the central atom nitrogen and the first carbon on the left, they both have sp3 hybridization orbitals because they both have 4 areas electron density around their central atom, resulting in tetrahedral electron pair geometry. Now we know the lone pair on nitrogen makes its molecular geometry look differently, but when it comes to hybridization and hybrid orbitals predicted, they would be the same because they have the same electron pair geometry, the difference we learned about in the previous chapter of sp3. sp3 is also the electron pair geometry associated around the central atom oxygen. Even though both there's 2 lone pairs and 2 bonding pairs causing the molecular geometry to be bent, we know that the electron pair geometry, not the molecular geometry, electron pair geometry is tetrahedral, the same as the nitrogen and the first carbon. If it's tetrahedral, if it has 4 areas, no matter whether they're bonds or lone pairs, they are going to form sp3 hybridized orbitals. The only one that's different in this molecule, the amino acid glycine, is the second carbon atom, central carbon atom. It has 3 areas of electron density, trigonal planar, therefore it has sp2 hybridized orbitals. Now you'll recall it will form sigma bonds between the carbon-carbon, carbon-oxygen, and the other carbon-oxygen, and a pi bond between the double bond of the carbon-oxygen. The sigma bonds are all in sp2 hybridized orbitals. The pi bond is the only one that's in that unhybridized p orbital of the carbon to the oxygen double bond. So in summary, valence bond theory, VB theory, uses VSEPR and hybridization of atomic orbitals to explain bond formation. Now, it can explain bonding only with compounds that brings in an even number of valence electrons. What if you have an odd number? We need to extend our understanding to include a theory called molecular orbital theory, or MO theory, and it basically results in the formation of molecular bonding orbitals that are either bonding or anti-bonding. One of the more positive aspects of molecular orbital theory, MO theory, is that it can help correctly predict whether a molecule is paramagnetic, having unpaired electrons, or diamagnetic, having paired electrons. So MO theory makes the assumption that when an element forms a bond, you form a new molecular orbital. Now this is not a mixing or hybridization of atomic orbitals as seen in valence bond theory. The electrons enter this newly established MO molecular orbital following Pauli exclusion principle, low energy first and then you fill according to low to high energy. In Hund's rule, follow Hund's rule that electrons will parallel spin in the same direction first and then the opposite directions. The key to MO theory is that comes from quantum mechanics and states that valence electrons are delocalized, meaning that the bonding electrons are not specifically above or below the plane of the bond as formed in valence bond theory, but they're in orbitals, molecular orbitals, that are spread over the entire molecule, again coming from quantum mechanics. Let's look at the molecule H2 and talk about atomic orbitals as seen for each hydrogen atom on the far left and on the far right, and in the middle, the creation of molecular orbitals. These are low and high energy orbitals called bonding of the low energy that are filled first, and anti-bonding that are filled next. As shown in the molecular orbital, the middle of the uh, graph chart, you see that the paired electrons go into the bonding orbital, forming a paramagnetic molecule where you have paired electrons. This is the particular usefulness of MO theory that more accurately predicts magnetism and bond strength.